Okay, the chain rule is used when you have two functions, f and g, both differentiable. And they're functions of x. So if you're taking, so y is defined to be the composition of f of g of x. That just means the input of f is the output of g. So you take x, and then your output for the function g is g of x. That becomes the input of f. So g is a function itself of x, but it's inside your f function, okay? And if you want to calculate the derivative of this composition, so d dx of this composition f of g of x, the chain rule says that you take the derivative of f evaluated at g of x, and then you multiply by the derivative of what's inside, in this case, g of x. Okay, so this is the chain rule. And if your function f is a power rule, then it's called the extended power rule. But f doesn't have to be a power function. It can be any function, really. And the chain rule will apply to that. So that's why I use the universal terminology of chain rule. Okay, so basically, you take the derivative of f, evaluate it at g of x, just like your original function is, but then the added step is you have to multiply by the derivative of what's inside. Okay, so let's do some examples. Let's suppose our function f of x is x squared and g of x is 2x minus 3. Then f of g of x, the composition function, we'll call that y, that is 2x minus 3 put inside f of x. So in other words, instead of x squared, we're going to have 2x minus 3 squared. Okay? That's our composition function. And to take the derivative of that, we are going to take our f function, evaluate it at g of x. So now I'm taking the derivative of my composition, dy dx, and I'm going to take f prime of x. Well, what's f prime of x? Since this is x squared, we can apply the power rule. We take 2 multiplied out in front, x, and then we subtract 1 from the power, which is just going to give us x to the 1, or just plain old x. So 2x is our derivative of x squared. We're going to take g of x and plug that into this function. See here, we're taking g of x and plugging it into the derivative. So this is going to be 2 times my input, which now is g of x. But by the chain rule, we have to multiply by the derivative of what's inside here. And the derivative of the g function is, this is a linear function. The derivative is just 2. So now we have to multiply. I'm going to do it in red just to kind of highlight the fact that we are multiplying by this 2 there. And to simplify this, we have that dy dx equals 2 times 2x Well, first let's do 2 times 2 is 4. So that's 4 times 2x minus 3. And then we distribute the 4. So we have 8x minus 12. And so this is the derivative of my composition. Okay. Here's the composition, 2x minus 3 inside the square function. F is the square function, g is the 2x minus 3. So this is the inside function, and I call this the outside function, if you will. Okay. Now, notice that this 2x minus 3 squared, I could have multiplied this out first and then taken the derivative using the power rule for polynomials. So let me show you another way of taking the derivative of this. Okay, so my composition function here becomes 2x minus 3 times 2x minus 3. And then using the FOIL method to multiply, I have 2x times 2x is 4x squared. Outside 2x minus 3 is negative 6x. I'm not minus 3, but times negative 3. And then negative 3 times 2x is minus 6x. Negative 3 times negative 3 is plus 9. Okay, so this simplifies as 4x squared plus 12x plus 9. And then taking the derivative of this dy dx would be, now I'm just using the power rule and the sum rule. 2 times 4 is 8x, right? I subtract 1 from 2. That just gives me 1. I don't have to write 1 there, but, and then the derivative of 12x plus 9, of course, is just 12 because this is a linear function. And you can see I got the same derivative as I did when I was using the chain rule. So in this particular example, it's not necessarily easier to use the chain rule. But you will see that it is very useful for other examples. And so let me do one like that. Any questions on this one? I don't want to go too fast. Give you some time to copy that if you need to. Just remember, you want to multiply by the derivative of the inside function. After you apply your derivative rules to the main part of the function, always remember to multiply by the derivative of what's inside. When I was a freshman taking calculus in college, I forgot to do that. And I thought I got an A on the test, but because I forgot that one little piece, I got a D instead. So I want to save you. I want you to learn from my mistake and don't do that, okay? Just remember, you've always got to multiply by the derivative of this inside function. So you take the 2 out front, multiply it, and then of course you subtract 1. So we're going to have 2x minus 3, but then multiply by the derivative of what's inside, okay? All right, example 2. So our function is y equals 3x minus 4 to the 4th power. And you can see we have a composition there. The main function that's working on this 3x minus 4 is the power of raising something to the power of 4, right? That's the main function. So f of x would be x to the 4th power, except now our x has a different function on the inside. X is replaced with 3x minus 4. So my my g of x, that's the inside, is the 3x minus 4. And the derivative of f is just 4x cubed, applying the power rule, right? I take 4 out front, subtract 1 from 4, that gives me the cube. And then g prime of x is simply 3, because this is a linear function and the slope is 3. So g prime of x is 3. So applying the chain rule to this, remember the chain rule just says that we have the derivative evaluated at g, so f prime of g of x multiplied by the derivative of what's inside the g of x there. So here's the rule that we're applying. So for this particular example, 4 comes out front. So I'm taking the derivative of this power function, so the 4 comes out front, and then I'm going to have that raised to the power of 3 because I subtract 1. But instead of f prime of x, I want f prime of g of x. So I'm going to take my g of x function and plug it in here. And I'm going to put that in blue. Okay, that's this function going in there. And then by the chain rule, I want to multiply by the derivative of this inside function, which is 3. Okay, so that is the application of the chain rule. The inside function gets plugged into the derivative, but then you got to multiply by the derivative of what's inside. Now, I could have multiplied this out first and gotten the same answer, but that would have been a lot of work. This is much easier. I would have had to take 3x minus 4 times 3x minus 4, and that would have been some quadratic function. Then I would have had to square that because I've got 4 copies, right? That would have given me 9 terms that I would have had to simplify. So that would have been a lot of algebra to do, but the chain rule here makes it pretty simple. So I'm going to go ahead and finish this off by multiplying 3 times 4, and I get 12 times 3x minus 4 cubed. And here's my derivative. All right, any questions on that? Again, this piece right here is what a lot of students, including me, when I was a freshman taking calculus, this is what students forget often, is to multiply by the derivative of the inside function. So I just really want to kind of emphasize that. Okay, we can kind of see what the inside function is. The inside function is x squared minus 3 because it's inside the square root function, right? So we think of our main function as the square root of some input x, and the inside function is x squared minus 3, and then the derivative. By the way, x, the square root function is the power x to the 1/2. Remember that from last time? So when you take the derivative, you're applying the power rule. You have to subtract 1 from 1/2, and that gives you negative 1/2. And if I simplify this, the 1/2 refers to the fact that I'm taking, or the square root in the denominator means I'm taking the square root. That's the 1/2. The negative means it's in the denominator. And this, of course, already is in the denominator, so it stays in the denominator. Okay, so this is my derivative of my main function. The inside function also has a derivative. So I'm using a power rule here. 2 comes out front, and then the power is reduced by 1, so then this new power is 1. Okay, so taking the derivative of this, again, I want to write it as x squared minus 3 to the 1/2 power. So dy dx becomes 1/2 times x squared minus 3. Subtracting 1 gives me negative 1/2. Then I should probably put this in blue so you can see how I'm substituting in here my g function. Okay, that goes in here. And then, so the f function derivative is 1/2 input to the negative 1/2. My input is the g of x, which is x squared minus 3. And then by the chain rule, I have to multiply by the derivative of this function, which is 2x. Okay? So that's where that all comes from. Try to highlight the fact that that's the blue marker there. That's coming from this. And then I simplify it. Notice that the 2's are going to cancel. This is 1/2 times 2. That's just going to be 1. So dy dx. This x is in the numerator. The 1/2 tells me that I'm going to take the square root, and the negative tells me it's going to be in the denominator. By the way, MyLab Math, when you do your homework, you don't really have to simplify it like I did here. You can just leave it like this, and they'll accept that as a valid answer when you're doing your homework. I don't know why they do that, because they're so picky on other things, but for some reason, when you're taking the derivative, they're much more lenient. This was as of last semester. I don't know if they've changed. You know, they're always making changes, but as of last semester, that was the case. So don't simplify it if it's just going to, you know, if you're going to make a mistake in the process of simplifying, then that's no good. So you don't have to simplify, at least for the derivatives. Unless it's multiple choice, in which case the answer may be simplified and you have to choose the right answer. So, but if you're just entering in the derivative, you know, just leave it in whatever form it's originally in. That way you're less likely to make a mistake if you're trying to simplify it. Okay, any questions on this one? All righty. Example 4. Our function is 4x to the 5th minus 5, and then that entire function raised to the power of negative 8. So we have a power function, a raising of your input to the negative 8, and then we have the input, another function, 4x5 minus 5. I'm not going to go through what I did writing f of x and f prime and all of that here, like I did in the first 3 examples. I'm just going to show you how I calculate the derivative. I'm applying the extended power rule in this case. That's what your textbook calls it, which is just another way of saying the chain rule for power functions. And when I find the derivative, I bring my power out front, as always. Then I take what's inside and raise it to the power that's 1 less than my original power. So I have negative 8 minus 1, right? And then by the chain rule, I need to multiply by the derivative of the inside function, which taking the derivative of 4x to the 5th minus 5 is 5 times 4 is 20, x to the 4th power, which is 1 less than 5. Okay, this is the chain rule. And of course, your textbook calls it the extended power rule. Now, to simplify this, I have -8 times 20, that's a -160, and then x to the 4th, times 4x to the 5th minus 5 to the -9th power. And you can leave it like that, or you can write it as -160x to the 4th over 4x to the 5th minus 5 to the 9th power. Moving it to the denominator, the power becomes positive, because this negative just means you take this whole thing and put it in the denominator. Okay. Any questions on that?
I have a question. Is there any way that you could go over what the f of x and the g of x?
This next problem is a little more involved because you have the added complexity of using the product rule. Okay, so we have the product of two power functions, which are in turn composition functions. So the first function is x plus 1 squared, which is a composition of the square function and with x plus 1. Then I'm going to take the product of that with another power function, which is 5 minus x cubed to the power of 5. So this also is a composition function. So we have 5 minus x cubed is the inside function, and that is raised to the power function of x to the 5th. Okay, so we have a lot going on here. We have kind of conceivably four functions. We have a function that's the square function. Let's say f of x is x squared. We have g of x is x to the 5th. And then we have the inside functions. Let's say h of x is x plus 1. And another one, k of x, 5 minus x cubed. Now, I'm not going to write that all out, but I am going to say, remind you from last time of the product rule. Okay, this is just from last week. We talked about the product rule, and I'm going to give you the rule to remind you. So if you have two functions that are multiplied together, then the derivative is just the first function times, first function times the derivative of the second plus the second times the derivative of the first. That's the product rule. So we're going to do that here. We're going to take dy dx, which is the first function, x plus 1 squared. And I'm just going to write the notation right now. I'm going to say the derivative d dx of the second function plus the second function times the derivative of the first. Okay. So let me review that. I'm applying first the product rule. The first function times the derivative of the second plus the second function times the derivative of the first. That's the product rule. Now, when I take these derivatives here, I'm going to have to use the extended power rule, because this is a power function. The power is 5. And this is also a power function. The power is 2. But because the inside functions are not x, just plain old x, they are themselves functions, we have to use the fact that we have to take the derivative of what's inside. So there's a lot going on here, but bear with me. Okay, so we have our x plus 1 squared. Now I'm going to take the derivative of 5 minus x cubed to the 5th power. I bring the 5 out front. I'm applying the power rule. Subtract 1 gives me a 4. And now by the extended power rule or the chain rule, I have to multiply by the derivative of this inside function. Well, this is just another power function here, negative x cubed. So the 3 multiplied by the negative and then x squared, because I subtract 1 from that 3 there. Okay? So this piece is the derivative of the inside function. And the outside function, remember, is just a power function. So you bring the power out front and then subtract 1, plus you're evaluating it at the inside function. Okay, so here's the power rule at work. Here's the chain rule at work. Now the next piece, I have this function here. Now I'm taking the derivative of this. So applying the power rule, the 2 comes out front, and then x plus 1 now is raised to the power of 1 because I subtract 1 from 2 to get 1. And then I take the derivative of what's inside. Well, the derivative of x plus 1 is just 1, right? Because this is a linear function with slope 1. So the derivative is just 1. I should probably write that in red because I want to emphasize the fact that this is the derivative of this inside function there. Okay? All right. Now I'm going to simplify it a little bit, not too much. And like I said, at least as of last semester, you could just leave it like this and it would take it as a valid answer. But I'm going to go ahead and simplify this. We have 5 times negative 3x squared is negative 15x squared times x plus 1 squared times the 5 minus x cubed to the 4th power. That's the first part. And then we're adding to that 2 times x plus 1 times 5 minus x cubed to the 5th power. And that is the derivative. So just to recap, my first observation is that this is a product. I have x plus 1 squared times 5 minus x cubed to the 5th power. So this is a product. I'm going to have to use the product rule. That is done right here. The product rule says when you take the derivative of a product, you take the first function times the derivative of the second, plus the second function times the derivative of the first. So that's what I did here. Now taking the derivative of these pieces right here, I have to use the extended power rule. So I take the power out front, 5, and then reduce the power by 1. So it becomes 5 minus x cubed to the 4th. And then by the chain rule or the extended power rule, I have to multiply by this derivative of the inside. Now the derivative here, again, 2 comes out front and I reduce the power by 1. Then I multiply by the derivative of the inside function, which just happens to be 1. Okay? And then here I simplify. Any questions on that one?
Can you go back 1 second?
So I'm going to first recognize that, well, I could use I could use the quotient rule, or I could use the power rule. I think the power rule would be easier here, so I'm going to do that. Because remember, when you see square root, you know that, oh, that's the power of 1/2. And when you see it in the denominator like that, you know that's a negative 1/2. So I'm going to look at this function as y equals 3x minus 5. This is my inside function, and the power is minus 1/2. That's how I'm going to view this. So I have a power function of raising it to the negative 1/2, and the input now is a function 3x minus 5, a linear function. So this is a composition, and I'm going to apply the extended power rule. The negative 1/2 comes out front. 3x minus 5 is then raised to negative 1/2 minus 1. Remember, you subtract 1 from your original power. And then the extended power rule or chain rule means I multiply by the derivative of what's inside. This is 3. Because this is a linear function, and the slope is 3. So the derivative of a linear function is its slope. This simplifies now as 3 times negative 1/2, or negative 3/2, times 3x minus 5 to the power of negative 3/2, because negative 1/2 minus 1 is negative 3/2. And so this then becomes, my numerator is negative 3, 2 is in the denominator, and so is this at 3x minus 5 to the 3/2. Because of that negative, it means it goes to the denominator. So this becomes 3x minus 5. The 3 means I cube it, and the 2 in the denominator of the exponent means I take the square root of that. Okay? So that's my derivative there. And notice this notation is interchangeable, right? dy dx could also be written as y prime. They mean the same thing. It's just a different notation. All righty. Any questions on that one? Okay. Example 7, we're just moving right along. Y equals x times x squared plus 1 to the 5th power. All right, we have another product there. So it's going to require us to use the product rule again. And remember, to find the derivative of a product, we take the first function times the derivative of the second function, which is x squared plus 1 to the 5th power, plus the second function times the derivative of the first. That's the product rule. And now to take the derivative here, we're going to use the extended power rule. This is a power function that is composed with another function, x squared plus 1. So the extended power rule, so we still have our x. Now to take the derivative of this thing, we bring 5 out front, and then we're going to take x squared plus 1 raised to the 4th power, right? Because I reduced this power by 1 to get 4. Then by the extended power rule or the chain rule, I have to multiply by the derivative of this inside function. So that is just going to be 2x. I'm just trying to highlight the fact that I'm doing that. Remember, this is the derivative of what's inside. Okay, now continuing. The derivative of x is just 1, right? So oh, wait a minute. I don't really want to put that like that. That's just 1 right there. There we go. All right. Simplifying this, which, like I said, I don't think you have to do that. We have 5x times 2x. That's 10x squared times x squared plus 1 to the 4th power plus 1 times this, which is just x squared plus 1 to the 5th power. And this is my derivative there. All right, I've done 2 examples using the product rule. Another rule that I introduced last time was the quotient rule. So I want to do an example that uses that. Any questions on this one before we move on? Okay. So we have a lot going on here. We have a power. The inside function is a quotient. It's a fraction x minus 5 over 2x plus 7. That is inside the square function. So you can see I'm going to need the chain rule here, or if you will, the extended power rule. And I'm going to go ahead and refresh your memory on the quotient rule, because when I take the derivative of this inside function, obviously I'm going to need the quotient rule. So to remind you, if you have a function y equals f over g, then the derivative y prime is the bottom function times the derivative of the top minus the top function times the derivative of the bottom, and then over the bottom function squared. Okay? That's the quotient rule. So taking the derivative here, this 2 is going to come out front, and then I have x minus 5 to the 2x, or divided by 2x plus 7 to the power of 1, right? Because I subtract 1 from my power when I'm taking the derivative. But then by the chain rule, I have to multiply by the derivative of this inside function. That's the chain rule, right? You have to take the derivative of what's inside and multiply your result by that, okay? Always have to multiply by that derivative. So now let's go ahead and calculate this derivative using the quotient rule. So dx of x minus 5 divided by 2x plus 7, okay, that is the bottom function times the derivative of the top. The derivative of x minus 5 is just 1, right? That's a linear function. Minus the top function times the derivative of the bottom. Here's another linear function. Derivative is 2. All divided by the bottom squared. Okay? So this is applying the quotient rule. Okay, so now when I simplify this, this becomes 2x plus 7 minus 2x minus 10, right? If I distribute this 2 here, it becomes 2x minus 2 times 5 is 10. But it's minus 2x minus 10, so that's going to be minus 2x plus 10 because I distribute the negative. And you can see that my 2x's are going to cancel. 2x minus 2x, those will go away. And this becomes 17, 7 plus 10, over 2x plus 7 squared. This is the derivative of the inside function, applying the quotient rule. So I'm going to replace this piece with my answer there. Okay, see, I'm just calculating the derivative right here. So I'm going to have 2 times x minus 5 over 2x plus 7 times this right here. Okay, so moving on. And we're going to have 2 times x minus 5 over 2x plus 7 times 17 over 2x plus 7 squared. And it looks like my numerator, 2 times 17 is 34. And then I've got x minus 5. Notice I have 2x plus 7 times 2x plus 7 squared. That's just going to be 2x plus 7 cubed. All right, so there is my final answer. So first I apply the power rule, bring the 2, subtract 1 from the power. Then the chain rule, take the derivative of the inside function, and then to calculate this derivative, I use the quotient rule. So there's a lot going on there, but this is a good example to show how all these rules work together. Okay, and just to remind you of the different rules, if you want kind of and I think I've done this before for you, is, let me share my screen. So if you if you type in your search basic derivative rules and then click on images, this chart right here is a really good one. These are all the rules that we covered. And these are the rules that are going to be on the first test for you to master these rules. You're also going to be tested on these rules when we get to the midterm exam. Okay? So you want to focus on them. Print this out if that helps. Here you can see we covered the chain rule today. And we covered this last week. So I want to do one more example from section 1.7 on the chain rule, and that is an application problem. So that'll be example 9. And we have a particle. The position of a particle is moving along a coordinate line. Okay, so a particle is moving along a line. The position is given by S equal to the square root of 82 plus 6t. T stands for time. S stands for position in physics. S is in meters. T is in seconds. Find the particle's rate of change at t equals 3 seconds. Okay, rate of change. When you see rate of change, we're not talking about average rate of change. Remember, the average rate of change is over an interval, so between 2 points, and you're calculating the slope of the secant line. The rate of change is actually the derivative of the function, and that is when that interval becomes collapsed down to a single point. And so you're talking about the rate of change at a point, in this case, t equals 3 seconds. So this is at an instant, not over an interval. So when you see just plain old rate of change as opposed to average rate of change, you're talking about the derivative here. So we need to calculate the derivative of S. Well, what is S? S is 82 plus 6t. This is a power function, right? To the power of 1/2. It's also a composition of 2 functions. The outside function is the square root function. The inside is 82 plus 6t. So we have a composition here. So we're going to have to use the extended power rule, which is just the chain rule applied to power functions. And so to calculate the derivative of S, we're going to take the 1/2 out front times the 82 plus 6t raised to the negative 1/2, because I have to subtract 1 from 1/2. That's how I got the negative 1/2. And then the extended power rule says I have to multiply by the derivative of the inside function. This is linear, right? This is 6 times my variable plus a constant. That's a line. So 6 is the slope, and that's the derivative of this inside function. So remember, you have to multiply by the derivative of what's inside. So I did that here. Simplifying this, I have 6 divided by 2, or 6 times 1/2, that's 3. And then 82 plus 6, 82 plus 6t to the negative 1/2, I can write this as 3 over the square root of 82 plus 6t. So the square root comes from the 1/2 there, and the negative just means it's placed in the denominator, right? The fact that this is in the denominator comes from that negative right there. So this is my final function for my derivative. But the question says find the particle's rate of change at t equals 3 seconds. So I want to calculate S prime evaluated at 3. And so I plug in 3 here. I get 3 divided by the square root of 82 plus 6 times 3. 82 plus 6 times 3, that's 82 plus 18, which is 100. The square root of 100 is 10. So this is going to be 3/10. And the rate of change would be in meters per second. Okay. There is a problem like this on the test, so make sure you know how to do this type of problem. And the next section that we're going to cover is section 1.8. Higher order derivatives. So the first derivative is when you just take your function and you find the derivative. So this would be the first derivative. This is the speed or the velocity Speed, of course, is just velocity in a line, and that's what we're talking about here, moving along a line. If you take the derivative of the first derivative, so you take the derivative once, but if you take the derivative of the derivative, that's the acceleration. So that's what we're going to talk about in section 1.8. We're going to talk about higher order derivatives. So let me go ahead and introduce that. I'm not going to cover the whole section today. I'm just going to kind of introduce it. So if you want to get started on the homework for section 1.8, you can. It's a real simple concept. I'm just going to do one example, but then I'll continue next time. Okay, so section 1.8. Is on higher order derivatives. So for example, if you have a function f of x is 2x to the 8th power. If I want to find the derivative of that, that's pretty simple. I take 8 times 2, that's 16, and then I subtract 1 from 8, that's 7. I don't need the chain rule here because there's no composition of a function. I've just got x to the power of 8. I don't have some other function here. So it's just applying the simple power rule, okay? This is the first derivative as opposed to the second derivative. The first derivative is just taking the derivative of your function. If you want to take the derivative again of the derivative of your derivative, then that's f prime prime, so f double prime. Now I'm taking the derivative of the derivative. So here's the derivative, 7 times 16, that would be 112. Then I'm subtracting 1 from 7, that's 6. So this is my second derivative. It's the derivative of the derivative. And that's what we mean by higher order derivatives. You can keep going, okay? You can take the derivative again, and then that would be f triple prime, if you will, okay? The notation that we use here is if y equals f of x and dy dx is f prime of x, then if you take the derivative again, whoops, d squared y dx squared, this just means I'm taking the derivative of the derivative, so that's f double prime. And you can keep going. So d to some power n of y dx to the n is just fn of x. And that's what I mean by higher order derivatives. You just keep taking the derivative and you can do it as many times as you want, okay? But that's just a sneak preview for next time that we meet. I'm going to go in more depth on higher order derivatives, and then we'll start reviewing for the exam, which is going to be next week. The exam is due Thursday. So I'll start reviewing on Thursday, and then on a week from today, so Tuesday, I'll continue reviewing, and then the test will be due Thursday at 11:59 p.m. So I'll send you an email with more information about that. So that's looking ahead to that test coming up. The test is going to cover sections 1.1 through 1.8, so all of chapter 1. Nothing from the review, okay? Although you want to at least be responsible for, you may have to apply the review concepts just because we do a lot of algebra, but I'm not going to ask you specific questions about the review that we did at the first 4 sections of this course. Okay, so any questions before we sign off here? That's all I have for today. So we get to finish a little early here. Thanks for joining. We'll see you on Thursday.